Hello everyone, I'm Jae-Yun Shim from Gwangju Institute of Science and Technology. Today I will talk about investigation of optimum machining conditions considering compliance of lapping wheel. My presentation will be proceeding like this sequence. From this page, I will show the introduction. The die and mold production process consists of CNC machining, manual lapping, and mold matching. However, due to labor-intensive industrial structure, it is hard to respond the labor cost increase and continuous high-skilled worker decrease. Therefore, we developed the automatic lapping machine containing 5-axis manipulator, path planning, vision and imaging unit, gantry and slide table, and auto tool changer. Among these, I play a role in development of path planning. However, due to non-linear compliance of compliant lapping wheel and concentrated wheel deformation time on the engaging and disengaging point of contact, the overmotion area occurred. In addition, this issue didn't be considered in previous researches that used the small size of mold because the path planning of small size of die mold is organized from outside to inside. On the other hand, path planning for post-process in large die mold is constructed from inside to inside so that it is the issue that must be considered. Therefore, to find optimum condition for path planning to reduce the overmachining, I set the two objectives, lapping simulation and improvement of surface uniformity. To predict the machined surface in lapping simulation, I studied for lapping wheel motion, compliance curve of wheel, and material removal model. And to minimize overmotion area and improve surface uniformity, I deal with a regression equation and optimum condition for surface uniformity. From now on, I will deal with lapping simulator design. This page shows the concept of lapping simulator. Normally, the amount of volume that the workpiece and tool overlap geometrically apply differently in cutting and lapping process. Among them, in cutting process, this overlapped volume is similar with swept volume of machining. However, in the lapping process, it is not equal to the amount of swept volume, but similar to the amount of wheel deformation. Through these characteristics, a basic concept in which the workpiece and lapping wheel geometrically overlap, as shown in the right figure, was constructed. In addition, I set the two considerations to reflect actual physical behavior of lapping process. First, it should be able to reflect the continuous machining force change due to the non-linear compliance at all numerical points. The second, it should be able to reflect complex and various shape of wheel and workpiece. Therefore, to satisfy previous concept and consideration, I designed detailed structure of a lapping simulator like this. Through these courses containing workpiece surface generation, cutter contact point generation, cutter location point generation, and velocity profiling, generate lapping wheel motion on surface. After that, through wheel deformation model and wheel compliance model, it made possible to predict the machining force of lapping process. And finally, by calculating the sliding velocity, or components of material removal model that derive the amount of machining and lapping process are satisfied. In here, there are two key points and differentiation. First, 3D wheel geometry-based wheel deformation model, which make it possible to reflect various wheel, workpiece, and quantity of wear. Second, compliance curve of compliant wheel that make it possible to predict the pressing force at transient section of wheel deformation. To confirm the simulation that I made, I conduct my simulation with these conditions. And this is my simulation. In the simulation, at first, we can see the overmotioned area in engaging section. Second, in linear section, we can see very steady motioned depths. After that, at last, in disengaging section, we can also see the overmotioned area. From the simulation, we can confirm that the simulation result adopting different compliance curve is much matched to experiment than constant compliance simulation result at engaging and disengaging section. In addition, the result table for depth of cut, we can confirm that the error value is smaller than 3 micrometer in all areas. From this page, I will show improvement of surface uniformity. In this chapter, to improve surface uniformity, I adopted the design of experiment. In this chapter, it starts from problem definition that define the factor and response. After that, we set the level of factors that show the limitation of factors. And through the factor limit and central composite design, the factor table is generated. The factor table generated in previous step is utilized as simulation. Through this, we can obtain factor and response table. Finally, we can derive the regression equation by using this table. And the regression equation can be utilized in response optimization and reaction surface. In this part, I will talk about the problem definition for depth of cut. The generated machining profile model contains complex shape of wheel and has the characteristics of cumulative machining. Hence, it is difficult to define single equation. For this reason, I adopted the design of experiment with these factors: pressing depth, linear velocity, and response depth of cut. And then I set the level of factors which are utilized in central composite design. In this part, to suppress overmotioning, I also utilize the design of experiment. The overmotioning at the lapping process is caused by deformation time assigned at the same engaging and disengaging point. Hence, to reduce assigned deformation time, I adopted the lamp shape of path planning to distribute the deformation time. So I set the factors pressing depth, linear velocity, engaging angle, and engaging velocity. And to predict the motion shape at engaging section, I utilize the RMS value, which use the steady point as a target value. Therefore, factor value having minimum RMS is optimum condition. And the working range of factors same like this table. To confirm the accuracy of regression equations, I set the 10 micrometer depth of cut as a target. In here, I firstly utilize the response optimization tool for depth of cut to find the factors that make the response fit to target. After that, calculated vector value is substituted to RMS regression equation. Through that, generate the reaction surface to find the factor values that have minimum RMS value. Finally, we can get the optimum condition for 10 micrometer machining. To confirm the optimum condition, I set the experimental setup like this figure with these conditions, which are same as optimum condition except for acceleration time 0.5 second. And then I conduct the experiment like this figure. First, The wheel comes close to surface with engaging angle 50.45 degree and engaging velocity 3.73 mm per sec. Second, in linear section, the wheel transport on surface with 7.6 mm per sec. And finally, the wheel is detached from the surface with same condition like first step. From the experiment, we obtained the machined surface and profile data at A-A cross-section. In addition, we can confirm that the deviation between actual and target in the section G1, G2, and G3 have the value within 2 micrometer. By summarizing my research, I make the 3 conclusions. First, a tool deformation model was produced using 3-dimensional shape of wheel and workpiece. So, it is possible to predict the shape of 3-dimensional surface. Second, engaging and disengaging curve of wheel compliance are applied. So, high accuracy simulation results are achieved. Finally, optimal modeling conditions are obtained through the engaging velocity optimization. So, it is possible to achieve high uniformity surface. Thank you for listening.